This is SpaceTime Series 25, Episode 14. Coming up on SpaceTime, growing debate about whether there's liquid water under the Martian South Pole, the Mars Ingenuity helicopter grounded by dust storms, and the Tonga volcanic eruption compared to volcanoes on the Red Planet. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Two separate studies have drawn opposite conclusions about the possible presence of liquid water reserves below the Martian South Pole. Finding water reserves on Mars is important, not just for future human colonies on the Red Planet, but also because it can be separated into its constituent hydrogen and oxygen components and used as a rocket fuel. And there's ample evidence that ancient Mars was a warm, wet world, with rivers and streams and even a massive northern hemisphere ocean. Orbital images show multiple signatures of landscapes carved by flowing water. There's evidence of beaches and seashore sedimentary deposits, and the unmistakable signs of riverbeds and deltas. And it's not just the orbital view. Rovers on the Martian surface have found geology chemically altered by water and river pebbles rounded by tumbling and fast-flowing streams. However, as Mars cooled and its core solidified, the planet's protective magnetic field began to shut down. Eventually, the relentless solar wind and radiation of space began eroding away the planet's atmosphere, slowly turning the red planet into the freeze-dried desert it is today. You see, as the atmosphere degassed into space and air pressure dropped, a significant amount of the red planet's water evaporated, with radiation then splitting water molecules in the upper atmosphere into separate hydrogen and oxygen atoms. And those lighter hydrogen atoms would then degas into space. But not all of Mars's water's gone. A lot of it still exists, locked away in minerals in the Martian crust or frozen in the Martian polar ice caps and as subsurface permafrost. And water still cycles on Mars, forming frost and ice in the winter and then sublimating into a gas during warmer periods. And occasionally, tantalizing signs of liquid water, usually in the form of a thick salty brine, are picked up by orbiting spacecraft. These are often in the guise of recurring slope lineae, that is, flows of water that seep out of the sides of cliffs during the warmer months, or in what appear to be brine moisture puddles formed in protected depressions on the surface. But the evidence for this liquid water is extremely sketchy. The recurring slope lineae could simply be sand and pebbles rolling down the slopes, and the moisture puddles could be caused by other chemistry. But some of the most promising signs for abundant liquid water on Mars have been signatures for what could be subsurface pools of liquid water below the polar ice caps. But even these are now open to interpretation. Back in 2018, scientists thought they were looking at liquid water when the European Space Agency's Mars Express spacecraft detected bright reflections under the red planet's southern polar ice cap using its Mars's subsurface sounding radar. Any near-surface liquid water would send back a strong bright signal, whereas the radar signature of ice and rock would be much smaller. So the radar observations look promising. But now researchers at the University of Texas in Austin claim the liquid water previously detected there is probably just a dusty mirage. The new findings, reported in the journal Geophysical Research Letters, suggest the reflections match those of volcanic plains which are found all over the red planet's surface. Scientists added an imaginary global ice sheet across a radar relief map of Mars. This imaginary ice sheet showed how Mars terrains would appear to radar when looked at through a mile of ice, allowing scientists to compare features across the entire planet with those under the ice cap. And they found bright reflections exactly like those seen at the South Pole, but scattered across all latitudes. And they matched where the volcanic plains were located. Now, at this point it's worth noting that here on Earth, iron-rich lava flows can leave behind rocks that reflect radar in the same way. Meanwhile, another study suggested the bright radar signatures could be a kind of clay which is made when rocks erode in water. The authors found that Earth-based clays reflected radar really brightly, just like the bright spots in the 2018 South Pole study. However, scientists from the Southwest Research Institute in San Antonio, Texas, say they've measured properties of ice-brine mixtures as cold as minus 98.3 degrees Celsius, which has helped confirm to them that salty water could exist between grains of ice or sediment under the ice cap of the Martian South Pole. They claim the exotic salts found on Mars have amazing antifreeze properties, allowing brines to remain liquid right down to minus 75 degrees Celsius. Their findings are based on over a decade of studies of Antarctic liquid ice subsurface lakes and modelling of how salts and brines would act in extremely cold conditions and in response to radar under Martian analogues. The authors measure the properties of perchlorate brines in an environmental chamber that reproduces near liquid nitrogen temperatures at Mars-like pressures. And the research shows that these brines could exist between grains of ice or sediments under the Martian South Pole. The debate continues. This is Space Time. Still to come, NASA's Mars Ingenuity helicopter grounded by a dust storm, and scientists have compared the Tonga volcanic eruption to volcanoes on Mars. All that and more still to come on Space Time. NASA's been forced to keep its Mars Ingenuity helicopter grounded because of a massive regional dust storm blanketing part of the red planet. The 19th flight for the tissue box-sized helicopter was planned for the start of the year. But Ingenuity weather forecasters at NASA's Jet Propulsion Laboratory in Pasadena, California, noticed signs of an approaching Martian dust storm and grounded the flight. Although only regional, mission managers have never seen a storm of this strength so early in the Martian year before. The problem is dust storms obscure the sunlight needed to power the aircraft's solar panels, resulting in an 18% drop in charge reaching the batteries. Also, the suspended dust particles are heated by the sunlight. That makes the air less dense, and that forces the helicopter's rotor blades to spin faster beyond safety limits in order to achieve lift. When it does fly again, Ingenuity will travel about 64 metres north back towards the mission's original February landing site. Scientists have been using Ingenuity to scout ahead of the Perseverance rover as it searches for signs of past or present microbial life on the red planet. The car-sized six-wheel Perseverance rover and the Ingenuity rotocopter will eventually travel about 2.5 kilometres further north to an ancient river delta. Scientists believe the delta is full of sedimentary material washed down from further upstream. Originally designed as a technology demonstrator, expected to only undertake between 5 and 7 flights over Perseverance's first month in Jezero Crater, the 1.8 kilogram aircraft has surprised everyone, functioning nominally for some 10 months now. This is Space Time. Still to come, the Tonga volcanic eruption compared to volcanoes on Mars, and SpaceX launches its 2000th Starlink satellite. All that and more still to come on Space Time. New satellite observations by NASA suggest that the plume blasted into the sky by the massive eruption of the undersea volcano near the tiny Pacific island nation of Tonga last month may have reached altitudes of between 40 and 50 kilometres, more than double the original estimates. The new data also suggests that the amount of energy released by the eruption was equivalent to somewhere between 4 and 18 megatons of TNT. Early estimates suggested the eruption was the most powerful on Earth in the past 30 years. NASA scientist Jim Garvin from the Goddard Space Flight Center in Greenbelt, Maryland, says the new estimates are based on how much material was blasted away, how resistant the rock was, and how high the eruption cloud was blown into the stratosphere at a range of different velocities. Garvin says the blast released hundreds of times the equivalent mechanical energy of the Hiroshima nuclear explosion. Satellite images caught the massive blast and shockwaves from space, and the sonic booms from the eruption could be clearly heard 2,300 kilometres away in New Zealand. Early estimates suggested the undersea eruption had a volcanic explosivity index, or VEI, of either 5 or 6. That's similar to the 1991 eruption of Mount Pinatubo and Krakatoa in 1883. The VEI scale, which is logarithmic, has a maximum of 8. Mount St. Helens was a 5. Garvin and colleagues were unusually well positioned to study the event. Ever since new land rose above the water's surface during an eruption in 2015, which joined two existing islands created during an earlier 2009 eruption, Garvin and colleagues have been monitoring the changes, using satellite observations and surface-based geophysical surveys. You see, this was the first volcanic island of its type to have formed and persisted in the modern satellite era, giving scientists an unprecedented view of its evolution from space. The Tonga volcano rises some 1,800 metres above the seafloor. It's some 20 kilometres wide and is topped by a submarine caldera 5 kilometres in diameter. The islands form part of the ring of the Hunga caldera. Now all the new land created during the 2015 eruption is gone, along with large chunks of the older 2009 islands which were part of the caldera's western and northern rim. Garvin and colleagues developed detailed maps of Hunga above and below the waterline. They used high-resolution radar from the Canadian Space Agency's RadarSat Constellation mission, optical observations from the commercial satellite company Maxar, and altimetry from NASA's ISAT-2 mission. They also used sonar-based bathymetry measurements collected by the Schmidt Oceanographic Institute in partnership with NASA and Columbia University. For the past 6 years, researchers from NASA, Columbia, the Tongan Geographical Service, and the Sea Education Association have worked together to determine how the young terrain was eroding due to the ongoing churn of waves and occasional battering by tropical cyclones. They also noted how wildlife, various types of shrubs, grasses, insects and birds, had moved from the lush ecosystems of Hunga Tonga and Hunga Hape and colonized the more barren landscape of the newer land. However, this all changed dramatically in January. For the first few weeks of 2022, the volcanic activity seemed typical enough, with intermittent small explosions of tephra, ash, steam and other volcanic gases, as magma and seawater interacted at a vent near the middle of the island. The ongoing eruptions were reshaping the landscape and continuously enlarging the island by adding new deposits of ash and rock to the growing volcanic cone. In fact, by early January, the island had expanded by about 60% compared to before the activity started in December 2021. The entire island had been completely covered by 1/10 of a cubic kilometre of new ash. But then, on January the 13th and 14th, an unusually powerful set of eruptions blasted ash surging into the stratosphere. Then, explosions on January the 15th launched material between 40 and 50 kilometres high, blanketing nearby islands with ash and triggering destructive 15-metre tall tsunami waves. Garvin thinks the massive eruption was caused by the hard rock of the foundation being weakened by earlier blasts. This then allowed the partial collapse of the caldera's northern rim, which in turn allowed the surrounding Pacific Ocean to rush into a high-temperature underground magma chamber. Now, the temperature of the magma usually exceeds 1,000 degrees Celsius. On the other hand, seawater is closer to around 20 degrees Celsius. So as you can imagine, the mixing of the two is an incredibly explosive event, especially in the confined space of a magma chamber. Garvin says these observations don't just teach scientists about extreme volcanism on Earth, but they're also windows on events on other worlds as well. These small volcanic islands, freshly made and evolving rapidly, are showing scientists the role that surface water would have played on Mars, and how they would have affected small volcanic landforms on the red planet. Garvin says images of the Martian surface are showing fields of similar-looking features in several regions. This report from NASA TV.
In early 2015, Earth saw the birth of a new island, the first of its explosive type in 53 years. The blast was so large that nearby tourists caught the explosion on camera. The new island, unofficially known as Hunga Tonga Hunga Hape, is located in the remote South Pacific, nestled between two other islands in the Kingdom of Tonga. It's the first island of its kind to erupt and persist in the modern satellite era, giving scientists an unprecedented view from space of its erosional evolution. The event immediately caught the attention of Dr. Jim Garvin, chief scientist at NASA's Goddard Space Flight Center, geomorphologist, and Mars expert.
It should be a pile of basaltic andesitic rocks. That's what you expect in this kind of setting. But there's more.
What does a Mars expert see in the island that the rest of us don't?
I think these small islands, small volcanic islands, freshly made, evolving rapidly, are windows into the role of surface waters on Mars as they have affected small landforms like volcanoes. And we see fields of them on Mars.
The island dramatically changed shape and size every day for the first few months. About 6 months in, it finally stabilized.
We watched this island change, and it got more and more exciting. It didn't wash away. While there was massive erosion, there was redeposition, protecting the island. Similar processes seen on Earth may have been at work 2 or 3 billion years ago on Mars. Persistent surface waters that may have fashioned the Martian terrain that is evident there today.
The truth is, the two systems are actually cosmically related. Our understanding of landforms on distant planets is directly informed by studying the evolution of similar features on Earth.
Earth is a magical place because really, it's our point of departure for everything. And we've come to realize in the last 100 years or so that it's a far more dynamic world than we ever thought.
This is Space Time. Still to come, SpaceX launches its 2000th Starlink satellite, and later in the science report, China says it will continue to upgrade its nuclear weapons arsenal. All that and more still to come on Space Time. SpaceX has successfully launched another 49 Starlink broadband internet satellites, bringing the total number flown to 2,042. The mission from Space Launch Complex 39A at the Kennedy Space Center in Florida was the 10th mission for the same Falcon 9 booster, making it the second Falcon 9 to have achieved 10 flights. The booster then returned to Earth, landing successfully downrange on a barge which had been pre-positioned in the North Atlantic Ocean.
Propellants have been loading on the vehicle since T-minus 35 minutes. Falcon 9 is a bipropellant vehicle, which means it uses 2 propellants, a fuel and an oxidizer. An oxidizer is a type of chemical that a fuel requires in order to burn. So for Falcon 9, our fuel is a refined form of kerosene known as RP1, and our oxidizer is a super chilled liquid oxygen, also called LOX. Now, the liquid oxygen is chilled well below its boiling point so that it becomes what we call densified. And this just means that it has a much greater amount of mass per volume and means we can load more of it into the booster. Additionally, Falcon 9 also needs an ignition source in order to go. And for that, we use the chemical TTEB, or triethyl aluminum and triethyl borane. Once it's fully fueled, Falcon 9 holds just over 1 million pounds of propellant that the vehicle will burn through in less than 3 minutes after liftoff. Currently, fuel is nearly fully loaded on stage 1 and already full on stage 2. Liquid oxygen is nearly full on stage 1 and about 80% on stage 2. Now, once all the tanks are full, both stages will continue to be topped off with liquid oxygen until T-minus 2 minutes to keep the temperatures as cold as possible. Now, in order to get these satellites into space, the rocket has to do more than just go up. It also has to go sideways really, really fast. So at liftoff, gravity is pulling straight down on the rocket. And as we ascend, we tilt the engines, technically called gimbaling, and that turns the rocket horizontally. We're still going up, but now we're also headed horizontally away from the launch pad. This is what we call a gravity turn. The rocket typically needs to go 17,500 miles per hour horizontally in order to avoid being pulled back down to Earth and actually get into orbit. To help demonstrate this concept, imagine firing a cannon from a really high mountain. The cannonball will arc, and then gravity will pull it down to Earth. As you increase the power, the cannonball will arc and land further and further away. Eventually, if you could continue to increase the power enough, the cannonball will be going so fast that it ends up in free fall around the Earth. Gravity is still pulling down on the cannonball, but it's going so fast that it never actually hits the ground. This arc, which constantly misses the Earth, is called an orbit.
Tanks are pressurizing for Stromback retract.
We are currently just under T-minus 4.5 minutes from liftoff.
Stromback retract has started.
Of our 36th launch of Starlink. And you just heard the call out that that truss structure, or the TE, has begun retraction. At this point in the countdown, both the first and second stages are nearly fully loaded with 1 million pounds of kerosene fuel and liquid oxygen. LOX loading has completed at T-minus 60 seconds. Falcon 9 will be in startup, so this means that the rocket's autonomous internal flight computers will have taken over the launch countdown. Starlink payload continues to be healthy, and Falcon 9 team is not tracking any issues at this time. We are moving into the terminal countdown.
Stage 2 LOX loads complete.
Finish the second stage liquid oxygen loading. We are now fully loaded with over 1 million pounds of kerosene fuel and liquid oxygen.
Falcon 9's in startup. Launch director, go for launch.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ignition and liftoff.
Vehicle is pitching downrange.
Stage 1 chamber pressure is nominal.
Falcon 9 has successfully lifted off from Launch Complex 39A at Kennedy Space Center, carrying our stack of 49 Starlink satellites to orbit. Moments ago, we throttled the engines down
Telemetry nominal.
in preparation for max Q, or maximum aerodynamic pressure, which will happen here in just a few seconds at T plus 1 minute and 12 seconds.
Falcon is supersonic, max Q.
We have just passed through max Q, and this is the maximum aerodynamic pressure that the stage sees. Next, we'll have 3 events happening in quick succession. First, we'll have main engine cutoff, followed by stage separation, and then second engine startup 1. Now, first main engine cutoff is where all 9 of those M1D engines on that first stage will shut off to slow the vehicle down in preparation for stage separation. This is where the first
engine chill has begun.
This is where the first and second stages will separate, with the first stage starting to make its way back to Earth for landing, while the second stage continues on its journey to the third event of second engine startup 1. And this is where that single MVAC engine on the second stage will light up and propel the second stage along with the Starlink satellites to orbit.
Nico.
Stage separation confirmed.
First stage and second stage tracker
Both stages
there.
are on nominal trajectories.
We did have successful MECO stage separation. There's fairing deployment there. SpaceX has reflown the Falcon fairing halves since November of 2019. Again, this was our second flight for both of those, and we will be attempting to recover them on our recovery vessel, Doug. Now, as stage 2 heads towards its targeted drop-off orbit there, stage 1 will execute 2 burns in order to make its way back home to Earth. The first is an entry burn. Now, this is where 3 of the M1D engines will reignite, and this helps to slow the stage down as it re-enters the upper parts of the Earth's atmosphere. Now, the second burn, of course, is the landing burn, and this is a single engine burn that brings the vehicle speed down rapidly in order to land on the drone ship.
Acquisition signal.
Stage 1 is currently making its way back to our drone ship, a short fall of gravitas in the Atlantic Ocean. Now, the Merlins on the first stage are optimized for sea level, so these achieve 190,000 pounds of thrust during ascent and descent. And in contrast, the MVAC engine is optimized for 220,500 pounds of thrust in vacuum. Now, the primary difference between these 2 engines is just the size of the nozzle. The MVAC nozzle is a lot larger than the M1D nozzles on first stage. Now, the Falcon 9 is equipped with 4 hypersonic titanium grid fins positioned near the top of the first stage, and the first stage is using these grid fins to help navigate and reorient itself as it heads back home to Earth. First stage also has an attitude control system, which you can sometimes see puffs of nitrogen gas coming from, and this attitude control system also helps that first stage orient itself as it returns home. We're just about 20 seconds from the start of our stage 1 entry burn, and this is a 20-second burn, and it'll help slow the vehicle down as it enters the thicker parts of the Earth's atmosphere. And this is a 3-engine burn, and it is 3 engines in a row on the first stage.
Stage 1 FTS is safe.
Stage 1 entry burn startup.
There's the start of the entry burn on the first stage. Those grid fins as the first stage is flying through its own plume there.
Stage 2 FTS is safe.
Stage 1 entry burn shutdown.
We did just have a successful stage 1 entry burn there. Now, coming up in just a few seconds, we will have the start of our stage 1 landing burn. This will be another about 20-second burn. Hopefully it will land us on our drone ship, a short fall of gravitas.
Stage 2, terminal guidance.
In the Atlantic Ocean.
Stage 1, startup.
Here's the start of our stage 1 landing burn.
Stage 1, landing leg deploy. Stage 1, landing leg.
Right there in the middle of the drone ship, we did just have the 103rd overall successful recovery of our first stage orbital class rocket.
Insertion.
And we just missed it there, but we did have a successful second engine cutoff, and we just got that confirmation of a good orbit from stage 2.
The launch came as a new study in the astrophysical journal Letters reported on the growing problems astronomers are facing because of the increasing numbers of Starlink satellites being launched. The authors found the satellite trains are causing thousands of streaks in their observations, affecting scientific research. They also confirmed that the number of images being affected is increasing with time as SpaceX deploys more and more satellites. SpaceX boss Elon Musk says he eventually hopes to have some 30,000 of the 260-kilogram satellites up in orbit. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favorite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more space time, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.